Good morning, ladies and gentlemen. Today we're going to discuss, to be a bit of a review, the electronics and electronic flow, electronic devices, electrical energy, how electricity flows, electrical safety, and several other key concepts involved with our electrical unit. Let's go ahead and get started with uh, a brief discussion of the history of electricity. Benjamin Franklin, key in determining that electricity and lightning were related. So Benjamin Franklin was not the first person who did experiments with electricity, right? But there was a key evolutionary link in the knowledge and the studying of electricity missing and why electricity acted the way it did, and was electricity and lightning, were they actually related? We know now they are, but Benjamin Franklin was key to determining that they were related and how they were related. All right, he made a famous discovery by putting a key on the end of a metal induction kite string. He basically tied a copper wire to the length of a kite string and the other end down to a makeshift capacitor, a very old school capacitor. What happened was he put that near some thunderstorm clouds in 1752, and he actually got very fortunate and caught lightning. And as lightning flew into and flowed into the capacitor, his experiment was a success, and he started to learn that the flow of electrons was not only in lightning but could possibly be harnessed for other things. Continuing on here. All right, so just moving on. Electricity is the flow of free electrons. Remember, electrical energy is nothing more than electrons flowing from an unstable position into a more stable position. That flow has to be made through conductors. Conductors are usually metallic. They some examples: copper, silver, aluminum, steel. Those are all good conductors. One of the best conductors out there is gold. That's why I have mentioned this before, but the airbags in a car are made, the sensors that the connection that makes sure the airbag will not fail, those connections are gold, so that when electrical flow needs to be through there, one thing gold doesn't corrode very easily. All right, but two, it's a great conductor, so they make them out of gold. All right, good conductors allow the flow of electrons through the material with very little resistance. Again, we have hit on this briefly, but good conductors don't conduct heat. They don't cause heat when electricity flows through them. Very poor conductors, like an oven eye, like the eye on an electric stove, those are poor conductors. So as you shove more and more electricity through there, they heat up. As a natural byproduct of that, resistance is heat. So that's how we cook food. That's how they get hot. They're not very good conductors. Good conductors like copper, gold, silver, aluminum. The power lines that we transmit electricity down, those are cool to the touch because they're such good conductors. They don't actually create very much heat. All right, we do need to make sure that we're always practicing electrical safety. It can have a devastating effect on the human body. Electricity is invisible, so it has no sound or smell, and it does travel at the speed of light. Once you've touched electricity and you've created the circuit, you've created a complete circuit allowing electricity to flow through your body. Even if you realize you've made a mistake by touching something, Your brain cannot respond quickly enough to prevent you from being shocked. Once you make the mistake of touching a wire that is charged and you have made yourself the connection, immediately you are going to be shocked. The speed of light is much, much, much quicker than your brain can process and make movements, or to tell your muscles to make movements. So once you touch that open wire, that power line that's down, once you stick something in an electrical socket, there's no coming back from that without getting shocked first. So we have to be very, very careful. All right, we never touch an electrical wire without making sure that it's first disconnected from the power source. All right, we never touch down power lines or wires that can be charged at any level, whether that's 110 to 120 volts on a house outlet, whether that's the car battery at 12 volts, but a higher amperage. We do not touch any sort of wire, any sort of electrical device that could shock us. If you don't know if that is turned off, just assume it's not and do not touch. Humans are very poor conductors. Our bodies are poor conductors. So when all that electricity flows through our body, it creates heat and burns the victim if you get enough voltage. For instance, the power line, if you were to touch those power lines at 10,000 volts or more, that's going to create a lot of electricity trying to flow through a conductor that's not great. When that happens, it's going to create tons of heat, and the product of which is going to burn you really bad. We would rather just not deal with that, so don't ever touch power lines that are down after a storm, or if a tree falls in them. Just don't. Just call the power company, turn and go the other way. All right, water and electricity never go together as well, and you need to keep them apart at all cost. We don't ever, if you see any sort of electrical appliances by water, immediately unplug them so that you don't accidentally touch them, because that will, because of the flow of electrons through that water, it'll spread that power out, and if you get a hold to that water at all, you'll complete the circuit. So never, ever, ever touch an electrical item to water. All right, back in a little bit with our history of electronics and electrical flow. As the flow of electrons began being harnessed in the late 19th century, our world became more and more reliant on electricity. When we start thinking about the Industrial Revolution, most of that would not have been possible without electricity. As electricity was studied, Thomas Edison patented the first light bulb in 1879, making our Industrial Revolution possible. It basically, if you think about it, it allowed people to work not only during the hours of the sun where they had light going through a window, but they could literally work all night, 3 shifts, 2 shifts a day, 24 hours a day. And our production has increased ever since. All right, that was in 1879. His invention, it took a lot of work, it took a lot of time, it took a lot of research. He tried thousands and thousands and thousands of mediums to go in that light bulb to be the filament. He finally found one that burned for just a little while. What he did is, what happened unsuccessfully for a lot of the time, was it would burn out. The filaments he tried to use, everything from horsehair to carbonized cardboard. What would happen is they would burn out. The electricity would try to flow, and it either was a very, very poor conductor, so it would stop the electrical flow, or it did conduct, but it wasn't a good enough conductor to do it without creating enough resistance. You had to have some resistance to turn that filament, to make that filament glow, to create light. You had to find the perfect amount of resistance in that material so that the light bulb would get hot enough to glow, but not get so hot that it burns straight through the filament, the little middle part in a traditional light bulb. All right, the conversion of electrical energy into light led the way for more recent electronic inventions that make our life more efficient. Everything from computers. We owe everything from computers to even our cars today, printers, refrigerators, cell phones. All those things can be traced back to this harnessing of electrical flow. Without it, nothing that works on batteries or house electrical energy, our voltage, our AC current, none of it would be there. All right, speaking of electrical flow, there's two basic types, and we discussed this, so this will be more of a review for you guys, but alternating current. AC current is current that reverses its direction many times a second at regular intervals, typically used in power supplies. When you plug something into a house electrical plug, you are using AC current. Anything from your computer, printers, we actually charge our cell phones with AC current, even though it goes through a bit of a regulator. All right. And the second type is DC current, direct current, which is an electrical current flowing only in one direction. We think of DC current being batteries. All right. Our batteries are direct current. It only flows in one direction uninterrupted until the battery is dead. All right, a couple more keywords and terms for us in our electrical units. Voltage and amperage are the two measures of current, which is the flow of electrons. We think of amperage as the strength of current, while voltage is thought of as more as the push that forces the flow of electrons through a medium. So when we're thinking, and this is something many people don't really realize, but voltage and amperage are two separate measures of basically the same energy. Voltage, if we can draw a distinction between the two, we think of voltage being the flow rate. Like if you put a buoy out into a river and you put a flow monitor on there, the flow over that buoy or around that buoy would be the voltage. But the current would be how much water is actually in the river. If we think about it in terms of amperage and voltage, we can think of it like this. This is the best example I could come up with at this time, but an example would be a fast-flowing river, which would be high voltage, but if it only has 3 to 6 inches of water, which means it would have a low amperage, it's not very deadly. However, the opposite, which would be a slow-moving river, that would be a low voltage, but the river 30 feet deep, which would be a high amperage, could still be very deadly. It would be very difficult to drown in water flowing 50 miles an hour, but that's only 3 to 6 inches deep. It would be you're probably not going to drown in that. All right, so it's not very deadly. However, a river 30 feet deep, even if it's flowing very, very slowly, which would be a high amperage, could still be very, very easy to drown in. All right, we've talked about this before as well, but high voltage is not what kills people in electrical accidents. It's the amperage. All right, a car battery is going to have more amperage at times than AC power coming through your house outlet. All right, so even a car battery, we don't think about that being just a deadly force, but it could really, really, really do some damage. Obviously, the most deadly would be a fast-moving river, high voltage, that was still really deep with a high amperage. So the combination of high voltage and high amperage would be by far the most deadly. All right. All right, and the final part of resistance, of electrical flow, is resistance. Resistance can be big. Think about a dam that's stopping a river from flowing completely. That would be known as an insulator. Basically, electrical current can't flow through there no matter how hard it tries. Resistance can also be small and just hinder the flow to protect more sensitive electronics. We've talked about LEDs many times from being destroyed by too much current. So at times, you need resistors. All right, electricity always tries to flow to ground. Electrical circuits have to be completed loops for electricity to flow through and power what items are inside the loop. Let's take a look at this example. We have a battery here, an electrical cell. All right, that power is flowing through a switch. When the switch is open, this would be an open switch, meaning the power is turned off. But if you close this switch here, connected to 2 points, that power would go right through the light bulb, which is acting as a resistor, and then it would go back into the negative side of the battery. All right, if we can look in another way on this B example here, we have a flow. These are using your IEEE symbols. All right, we have a battery power. All right, it's going to flow out. It's going to go through the switch, again through the light bulb as an insulator. This is a conductive wire. We would think usually probably copper, and then back into the battery. All right, two types of circuits. You have series. This would be a series circuit. Remember, series circuits are single path circuits. All right, we have a battery here again. That battery is going to flow through one path. You'll see here, one path. As it hits the resistors, the light bulbs, there's two resistors in here because there's two bulbs. It's going to go through one light bulb. It's going to step down, go to the second light bulb. Theoretically, the second light bulb is going to burn at least fractionally dimmer than the first one. After it leaves the second resistor, it's going to flow back into the cell. So in our schematic drawing, we have a battery here, a bulb, and then back. There's no inline resistor in here other than the light bulbs. All right, and then we have parallel circuits. So in our parallel circuits, we have a battery again. We're going to flow that electricity through two paths. You have path one here that's going to one light bulb, all right, or the battery power is going to bypass the first path. Since both of them are completed circuits, it can go straight through path 2, straight through the light bulb, and then back as well, and the power will recollect on the E wire here, and then straight through back into the battery. If we can schematically do it, we have our IEEE symbol for our power source here, a battery. We go path 1, path 2, through 2 light bulbs, and the other way. Now you might say, what's the advantage of having a parallel circuit? It does look harder and more complicated, and maybe it is to wire up. However, let me show you a clear advantage. In a series circuit, once this light bulb burns out, the flow is going to be stopped completely. All right. Once this one burns out, if this one goes first, the battery's connection is going to be broken completely. So both bulbs are going to not shine anymore if anything happens to either bulb. If we go back to our example of a parallel circuit, let's say bulb 1 here, we'll nickname this one bulb 1. Let's say it goes out. Power is still going to flow through the B line and then through number 2, bulb 2, and then back. So this bulb could burn out and this one will still keep shining, which is why in your house, every time a light bulb goes out, it doesn't shut an entire run of light bulbs out. All right, or this one could go out and bulb 1 be still shining. All right, I'll give you an example. Your house is wired in parallel. All right, an example of what happens when one bulb does go out and it creates and it kills a whole series. You can think of Christmas lights, the light bulbs in there, the way Christmas lights are lit up. They are powered in series, meaning when you have one light bulb that goes out, and everybody's experienced this, it's the most frustrating thing ever at times, but you have to find the one bulb that went out because it's messing up the entire rest of the strand of lights. All right, so keep that in mind when we're thinking about electricity.